All right. Chapter 15, which is smart pointers. Let's get it. Smart pointers. A pointer is a general concept for a variable that contains an address in memory. This address refers to or points at some other data. The most common kind of pointer in Rust is a reference, which you learned about in chapter 4. References are indicated by the AND symbol and borrow the value they point to. They don't have any special capabilities other than referring to data. Also, they don't have any overhead and are the kind of pointer we use most often. Okay, so we already learned about pointers, seemingly in chapter 4, when we started using the AND. Pointer. Nothing special about that. Smart pointers, on the other hand, are data structures that not only act like a pointer does, but also have additional metadata and capabilities. The concept of smart pointers isn't unique to Rust. Smart pointers originated in C++ and exist in other languages as well. In Rust, the different smart pointers defined in the standard library provide functionality beyond that provided by references. One example that we'll explore in this chapter is the reference counting smart pointer type. This pointer enables you to have multiple owners of data by keeping track of the number of owners and, when no owner remains, cleaning up the data. Okay, so what they're saying here is, 1, smart pointers are not unique to Rust. They've existed in C++ and other languages as well. But more importantly, smart pointers are data structures that act like pointers, but they also have additional metadata. And one they're going to reference, at least in this section, seemingly is the reference counting one, where you can have, this pointer enables you to have multiple owners of the data. And then once all the owners are gone, it seemingly just cleans up itself. In Rust, which uses the concept of ownership and borrowing, an additional difference between references and smart pointers is that references are pointers that only borrow data. In contrast, in many cases, smart pointers own the data they point to. Ooh, I see. So with the AND symbol that we learned in chapter 4, those references only point to borrowed data, or they only borrow data, right? But smart pointers usually, or typically, own the data they point to, which is very different. We've already encountered a few smart pointers in this book, such as string and vec, in chapter 8. Although we didn't call them smart pointers at the time, both these types count as smart pointers because they own some memory and allow you to manipulate it. They also have metadata, such as their capacity, and extra capabilities or guarantees, such as with string ensuring its data will always be valid UTF-8. I'm going to need to continue reading because I'm not exactly sure how string and vec are smart pointers. I mean, I guess they do point to other data. Like string points to another string and then has, like they said, it does have the extra capabilities where you can ensure the capacity. And string, from my understanding, is a vector of bytes that adhere to UTF-8. So as long as vec is a smart pointer, string should definitely be a smart pointer. So it does make sense, but still, I'm kind of fuzzy on that. Smart pointers are usually implemented using structs. The characteristic that distinguishes a smart pointer from an originary struct is that smart pointers implement the deref and drops traits. The deref trait allows an instance of a smart pointer struct to behave like a reference, so you can write code that works with either references or smart pointers. The drop trait allows you to customize the code that is run when an instance of a smart pointer goes out of scope. In this chapter, we'll discuss both traits and demonstrate why they're important to smart pointers. So here they tell you the things that are needed to implement a smart pointer. And smart pointers are structs, ordinary structs, but they implement both the deref and the drop trait. Now the drop trait we know about. That is the trait that allows you to, like when you come out of a code block, it drops it, the reference. Deref sounds like it's just a reference pointer, but I'm not sure. You'll see. Given that the smart pointer pattern is a general design pattern used frequently in Rust, this chapter won't cover every existing smart pointer. Many libraries have their own smart pointers, and you can even write your own. We'll cover the most common smart pointers in the standard library. Box for allocating values on the heap. RC, a reference counting type that enables multiple ownership. Ref and ref mutable, access through ref cell, a type that enforces the borrowing rules at runtime instead of compile time. In addition, we'll cover the interior mutability pattern, where a immutable type exposes an API for mutating an interior value. We'll also discuss reference cycles, how they can leak memory and how to prevent them. Let's dive in. Wow. So in this chapter, we're going to be covering the basics of smart pointers, at least the most common ones that are used. We have box for allocating values in the heap. We have RC for reference counting, which enables multiple ownership, which they mentioned previously in this blob of text. And then here, which I'm not too sure about, we have ref cells, which allow you access to ref and mutable ref, which, according to this text, allows you to enforce borrowing rules at runtime instead of compile time. And then also they're going to teach us how to do interior mutability, which allows us to take a immutable type that exposes an API for the interior value and mutate the interior value. That sounds kind of meta. Let's see what happens. Using box T to point to data on the heap. The most straightforward smart pointer is a box, whose type is written box T. Boxes allow you to store data on the heap rather than the stack. What remains on the stack is the pointer to the heap data. Refer to chapter 4 to review the differences between the stack and the heap. So just a quick definition. They say that the box type is straightforward, box T, and this allows you to store data on the heap rather than the stack. And then the pointer to the data on the heap, that it is on the stack. Or I should say that the pointer to the data on the heap, that remains on the stack. Boxes don't have performance overhead other than storing their data on the heap instead of the stack. But they don't have many extra capabilities either. You'll use them most often in these situations. When you have a type whose size can't be known at compile time and you want to use a value of that type in a context that requires an exact size. Okay? When you have a large amount of data and you want to transfer ownership but ensure that the data won't be copied when you do so. Make sense? When you want to own a value and you care only that it's a type that implements a particular trait rather than being a specific type. I see. Okay, so what this is here they just state the generalities of a box. It doesn't have many capabilities outside of making a pointer to something on the heap and then storing that pointer on the stack. But the situations in which you would use this are situations where this is useful are listed here. The first one's pretty straightforward. Whereas you have something of a type whose size can't be known at compile time. So because it can't be known at compile time, that means that that data is being stored in the heap because it needs to be able to grow in size, right? And then if your code requires some type of context where it needs to know the exact size, well, if it can't be known at compile time, then the compiler can't check it. So then you have to use another means. So that makes sense. This is probably just to get around Rust errors, get around the compiler. That makes sense. And then the second case, when you have a large amount of data that you want to transfer ownership, but ensure that the data will not be copied. This makes sense because instead of copying the data, you just create a pointer that references that data. Okay, yeah. Straightforward. Okay, now this third example, something I'm not too familiar with. It states, when you want to own a value and you care only that it's a type that implements a particular trait rather than being a specific type. Hopefully they cover that scenario, because off the top of my head, I don't know. We'll demonstrate the first situation in the enabling recursive types with boxes section. In the second case, transferring ownership of a large amount of data can take a long time because the data is copied around on the stack. To improve performance in this situation, we can store a large amount of data on the heap in a box. Then, only the small amount of pointer data is copied around on the stack, while the data it references stays in one place on the heap. The third case is known as trait object, and chapter 17 devotes an entire section using trait objects that allow for values of different types, just to that topic. So what you learn here, you'll apply again in chapter 17. So they kind of validated me not knowing anything about this, because it's seemingly a very big topic that is not straightforward and that has its own chapter, or at least its own section in chapter 17, which is 2 chapters away. So yeah, we're not going to learn anything about the third case. Well, at least not until chapter 17 anyway. Moving onward. Using a box to store data on the heap. Before we discuss this use case for box, we'll cover the syntax and how to interact with values stored within a box. Listing 15-1 shows you how to use a box to store an I32 value on the heap. And that's all they have there. So let's open the my editor real quick. See what they have. They have let b equal box. I do not have to import it, so it seems like it's already here. New 5. And then print line b equal terminal cargo run. Warning, b equals 5. Close this. Okay. So that worked. We define the variable b to have the value of a box that points to a value 5, which is allocated on the heap. This program will print b equals 5, which we verified right here. In this case, we can access the data in the box similar to how we would if the data were on the stack. Just like any own value, when a box goes out of scope, as b does at the end of main, it will be deallocated. The deallocation happens for the box, stored on the stack, and the data it points to stored on the heap. I see. So that is good to know. So what they're stating here is just the basic code, but the important parts are that 1, we define a box, we have the value in here, and it created both a pointer reference that's going to be stored on the stack, and 5, the actual value is going to be stored in the heap. But what we want to note is that when the reference b goes out of scope, it gets deallocated, and this means, at least in this scenario, that both the pointer on the stack and the data it points to on the heap are both going to be deallocated. That's good to know. Putting a single value on the heap isn't very useful, so you won't use boxes by themselves in this way very often. Having values like a single I32 on the stack where they're stored by default is more appropriate in the majority of situations. Let's look at a case where boxes allow us to define types that we wouldn't be allowed to if we didn't have boxes. So here they're just stating that the example above, this b new 5 thing, is very contrived and doesn't make any sense in terms of context and practicality, but it does demonstrate the use of box. The reason why it is not useful in terms of practicality is because 5 is I32 value, which is stored on the stack, and then copying is easy. It's just a copy. They do it for us automatically. It makes no sense to use a box to put this data on the heap. But they're going to go into an example where using box is what is needed. And that is enabling recursive types with boxes. At compile time, Rust needs to know how much space a type takes up. One type whose size can't be known at compile time is a recursive type, where a value can have as part of itself another value of the same type. Because this nesting of values could theoretically continue infinitely, Rust doesn't know how much space a value of a recursive type needs. However, boxes have a known size. So by inserting a box in a recursive type definition, you can have recursive types. So one thing they did in this section was they defined what a recursive type is. And that's where a value can have as part of itself another value of the same type. So let's say you have type X here, right? And then within type X, you have another type X, XXX, all the way going down, right? In theory, the size of that can be infinitely long or infinitely large. And the definition can go infinitely long, right? Because it's recursive. Rust at compile time needs to know the size or the amount of space your data type takes up. Because it can't, you in theory cannot directly define a recursive type. However, you can if you use boxes, because box seemingly has a definitive size at compile time, which they state right here. Boxes have a known size, so by inserting a box into a recursive type definition, you can have recursive types. In theory, that makes sense. So let's see how it goes. Let's explore the cons list, which is a data type common in functional programming languages as an example of a recursive type. The cons list type we'll define is straightforward, except for the recursion. Therefore, the concept in the example we'll work with will be useful anytime you get into more complex situations involving recursive types. I'm not sure what a cons list is. They said it's common in functional programming languages. I don't program in any. And it's recursive. So let's see what information they can tell us about it. More information about, this is kind of big. Let me just expand it. More information about the cons list. A cons list is a data structure that comes from the Lisp programming language and its dialects. In Lisp, the cons function, short for construct function, constructs a new pair from its two arguments, which usually are a single value and another pair. These pairs containing pairs form a list. The cons function concept has made its way into more general functional programming jargon. To cons X onto Y informally means to construct a new container instance by putting the elements X at the start of this new container, followed by the container Y. What? This is sort of making sense. So let's just rehash what we have here. We have a cons list, which is a data structure. It's short for construct function. And what it seemingly does is, so I've seen Lisp before. I've seen a Lisp dialect, and the way you define things, we have like your parentheses, and you have the, let's say, operator, and then you have the two things it's operating on, but they're nested within each other, and you can continuously go on and on and on. That's seemingly what the cons list is. It's just the way they write their functions. So for example, you can con X into Y, which informally means you can have the construct container of element X, which could be an expression or an operator, at the start of the new container, followed by the container Y. I'm sort of getting the gist of it, but at the same time, don't quote me on this. Each item in a cons list contains two elements, the value of the current item and the next item. The last item in the list contains only a value called nil, without a next item. Hold on, let's just reference this. Wikipedia cons list. Okay, so I get the general gist of it. So in our book, what they're defining is just a generic cons. For example, here's a list, right? You could write it this way: cons 1, cons 2, cons 3, and then nil. Nil being the last part, the end of recursive functionality of it, which shorthand is a list of 1, 2, and 3. So in the cons onto x, x cons x onto y syntax, that'd be cons 1 onto 2, which then cons 2 onto 3, which then cons 3 onto nil, which is a stopping point for recursion, because recursion needs a stopping point in order to not go on indefinitely. So we can just think of this in our head. Cool, that makes a lot more sense now. Let's go back to this. Each item in a cons list contains two elements: the value of the current item and the next item. The last item in the list contains only the value. The last item in the list contains only a value called nil without a next item. A cons list is produced by recursively calling the cons function. The canonical name to denote the base case of the recursion is nil. Note that this is not the same as the null or nil concepts in chapter 6, which is an invalid or absent value. Alright, cool. So here's where they round it off, and I think I closed that tab. I'm not exactly sure why. So let me just open it again. So again, we're thinking about this concept, right? We have cons, and we have the outer parentheses here. And then within it, we have the next value, which within it defines the next value. And you always have the start value, and you have the next one. And here, the next value is nil, which is the base case for the recursion. And a base case for recursion is, like I said earlier, the stopping point of where we stop doing the same call over and over and over again, where the recursion stops. You can think of it that way. And what they just noted is that this nil is different from the nil that was talked about in other chapters. Although functional programming languages use cons lists frequently, the cons list isn't a commonly used data structure in Rust. Most of the time, when you have a list of items in Rust, vect is a better choice to use. Other more complex recursive data types are useful in various situations, but by starting with the cons list, we can explore how boxes let us define a recursive data type without much distraction. And listing 15-2 contains an enum definition for a cons list. Note that this code won't compile yet because the list type doesn't have a known size, which we'll demonstrate. Sure, why not? Come down here. So seemingly, I can try to talk and type at the same time. Actually, I can't. What we're doing here is we're writing the exact thing that we saw here. Right here. We're recreating a list using cons. Should be pretty straightforward, hopefully. So we define cons, which I guess is a thing. I32, and then the recursive part, list, and then nil. Okay, and this should not compile. Verify that. But I am curious as to what it tells me. Recursive type list has infinite size, which currently it does because it's nested within each other. So you can have a list, and then in that list you can have another list, in that list you can have another list, and it has no stopping point. And because we don't know what's in it, we can't define the size, or the compiler doesn't know the size at runtime. All makes sense. Cool. Note, we're implementing a cons list that holds only I32 values for the purpose of this example. We could have implemented it using generics, as we discussed in chapter 10, to define a cons list type that could store values of any type. Alright, so what they're saying here is just a small disclaimer. In this example, because it's just an example, we want to make it easy, we're using I32, which means that our end result will only be able to store I32 values. However, if we wanted to, we could have used generics, which then would allow us to write this once and be able to store any type of struct type in it. Using the list type to store the list 1, 2, 3 would look like the code in listing 15-3. And let's... Oh, we have to import it. I see. Okay. So use create list, which comes up, cons nil. Alright, cons and nil are now imported. We have our enum list, which already was defined. And then if we wanted to create a list of 1, 2, 3, it will look like this. Equals cons 1, and then here cons 2, cons 3, and nil. So we know that's not going to compile because this doesn't compile yet. We're not using boxes yet. The first cons value holds 1 and another list value. The list value is another cons value that holds 2 and another list value. The list value is one more cons value that holds 3 and a list value, which is finally nil, the non-recursive variant that signals the end of the list. If we try to compile this code in 15-3, we get the error shown in listing 15-4, which is what we already saw. The list has infinite size. Recursive without indirection. This part is probably pointing to the need of a box, and then you have the help, which is also here, right? Recursive without indirection, which means you need some sort of indirection, which points to a reference of some type. And they have the help, which says use box, RC, or a pointer. Yeah. So the help, the error message is actually really useful in this case. The error shows that type has infinite size. The reason is that we've defined list with a variant that is recursive. It holds another value of itself directly. As a result, Rust can't figure out how much space it needs to store a list value. Let's break down why we get this error a bit. First, let's look at how Rust decides how much space it needs to store a value on a non-recursive type. So here they're just going over the error, and they stated, like I stated earlier, the compiler, or Rust at compile time, does not know the size of the list because it's recursive. And then now we're going to diverge for a second and figure out how Rust decides how much space to give a non-recursive value or type. Computing the size of a non-recursive type. Recall the message enum we defined in listing 6-2 when we discussed enum definition in chapter 6. And we had a message enum, and we had the different variants. The variants were quit, move, write, and change color. To determine how much space to allocate for a message value, Rust goes through each of the variants to see which variant needs the most space. Rust sees that message quit doesn't need any space. Message move needs enough space to store 2 I32 values, and so forth. Because only one variant will be used, the most space a message value will need is the space it will take up to store the largest of its variants. I see. So in terms of enums, what they're stating here is that in order for Rust to figure out how to store it, they need to figure out which variant of the enum is the largest. And then make sure they have enough space for that largest variant, which seemingly should be, I want to say it's string, because I mean string is pointer on the heap, but it could be changing color. Either or, Rust is going to figure out which one is the largest and then allocate enough space for that the largest can be stored, and as such it follows that all of these smaller variants can still be stored in that allocated space. Contrast this with what happens when Rust tries to determine how much space a recursive type like the list enum in listing 15-2 needs. The compiler starts by looking at the cons variant, which holds a value of type i32 and a value of type list. Therefore, cons needs an amount of space equal to the size of i32 plus the size of a list. To figure out how much memory a list type needs, the compiler looks at the variant starting with the cons variant. The cons variant then holds a type of i32 and the type of list, and this process continues infinitely, as shown in figure 15-1. So what they're doing here is they're verbalizing why this recursive data type is infinite. And they have this nice little diagram that demonstrates it. Just the nesting all the way down. Using box to get a recursive type with a known size. Rust can't figure out how much space to allocate for recursively defined types, so the compiler gives the error in listing 15-4. But the error does include this helpful suggestion. And help, insert indirection, box, RC, and just to make this representable. In this suggestion, indirection means that instead of storing a value directly, we'll change the data structure to store the value indirectly by storing a pointer to the value instead. Because a box is a pointer, Rust always knows how much space box needs. A pointer size doesn't change based on the amount of data it's pointing to. This means that we can put a box inside the cons variant instead of another list value directly. The box will point to the next list value that will be on the heap rather than inside the cons variant. Conceptually, we still have a list created with lists holding another list, but this implementation is now more like placing the items next to one another rather than inside one another. I see. This is the missing piece of the puzzle. This is the information that we needed to know. So the reason why any of this works is because pointers are always of a fixed size. Rust, the compiler, always knows the size needed to allocate to a pointer. As such, if we put all of our cons within a box, then, well, that data, the list data is going to be stored in a heap, and that can be variable in size. We don't care about that. But we know that the pointer is a fixed size, and thus the compiler can then adequately, not error out and allow us to continue, which in a sense just allows us to do this recursive definition. Conceptually, what they try to explain it as is, instead of thinking of it as putting a data type within a data type, we're putting these data types next to each other and having a pointer just point arrows to the next one in the list. We can change the definition of the list enum in listing 15-2 and the uses of the list in listing 15-3 to the code in list 15-5, which will compile. And this is what we've been waiting for. i32 box. And this is seemingly all we had to do. Oh, well, no, we have to put these in boxes too. Enter box. And we already know how to define it. Cons box new box new, and we need 1, 2, 3. Was it? Quite possibly. Let's see if I have all the parentheses correct. Yeah, everything's correct. It compiled, it ran. I didn't print anything to screen. Cool. So this worked, and all we really did was we have the enum, we have the variance, cons and nil, right? And within cons, instead of defining it as I32 and list, which is this enum, we put that list into a box, which is now a pointer to the next item, the next list. Which makes, in terms of the compiler, this makes this a definite size at compile time. And this we can continue writing the program. That's cool. Also, you put this down here, which I didn't really explain this properly earlier, but it's crate as in this crate, list as in this variant, and then it's importing the two variants, cons and nil. And the reason why we're doing this is so that we don't have to write list : cons or list : nil here. This is just a local import of this. I moved this at the top because I like my imports at the top, but yeah, you can put it there. The con variant will need the size of an I32 plus the space to store the box's pointer data. That's it. This is it. This is the new construct. The nil variant stores no value, so it needs less space than the con variant. We now know that any list value will take up the size of an I32 plus the size of a box pointer data. By using a box, we've broken the infinite recursive chain so the compiler can figure out the size it needs to store a list value. Figure 15-2 shows what a cons variant looks like now. This is it, a box, so a pointer. Boxes provide only, oh, this is the end of it. Let me just make this bigger. Boxes provide only the indirection and heap allocation. They don't have any other special capabilities like those we'll see with the other smart pointer types. They also don't have any performance overhead that these special capabilities incur. So they can be useful in cases like the cons list where the indirection is the only feature we need. We'll look at more use cases for boxes in chapter 17 too. The box type is a smart pointer because it implements the deref trait, which allows box values to be treated like references. When a box value goes out of scope, the heap data that the box is pointing to is cleaned up as well because the drop trait implementation. Let's explore these two traits in more detail. These two traits will be even more important to the functionality provided by the other smart pointer types we'll discuss in the rest of the chapter. And that's the end of the chapter. That was very interesting for me. Wow, this indirection. I'm looking forward to the next section. I hope you liked the video. If it was entertaining, give it a thumbs up, like, subscribe. Outside of that, peace.